So in the previous video, we were able to kind of derive these three equations over here that can essentially describe the velocity and acceleration of a particle or a body in terms of the derivatives of position, right? And so, we just used our basic principles from, physics in high school in grade 9 and 10 in order to actually derive these different equations over here to figure out the instantaneous velocity and instantaneous acceleration. And so what we're actually going to do in this video is apply these notions to motion graphs. So I essentially just took the same kind of graph that we used in the previous example right over here, kind of just copy pasted it down here. And essentially what we're going to do is we're going to try to kind of analyze the velocity of this kind of particle using the graph, the instantaneous velocity at different points, and the notion that the instantaneous velocity is given by the derivative at that particular point. And so let's actually go ahead and try to do that. So let's start off with this point right over here. This point looks to be kind of a local maximum, right? So this point, it seems as though the tangent line looks flat, right? It looks to be like a horizontal tangent line at this particular point. It's a maximum. We're going to later on learn why that is, why it is that at maximum points the derivative is equal to 0. But it looks as though we have a maximum over here. And so that tells us that since the slope of the tangent line is flat, that at this instant, our velocity is equal to 0. So right over here, the velocity is equal to 0, which tells us that at this moment, our particle isn't moving, right? So if this x of t represents kind of a particle floating around in space, then at at this particular point, v is equal to 0. So our particle is not moving. And, a similar logic could be used for this point right over here. It looks as though the tangent line is kind of a horizontal flat line at this particular instant in time. And so over here, we also have that v is equal to 0. But then let's go ahead and take a look at some other points. Let's say maybe this point right over here. If we were to approximate the tangent line, it may look something like this, right? And so this tangent line obviously has a positive slope, like it looks to be increasing, right? It's a linear function with a positive slope. And because of the fact that the slope of the tangent line is positive, that tells us that the derivative is positive at this point. But what is the derivative of position? Well, that's just going to be velocity, right? So here we can say that the velocity is going to be greater than 0, right? It seems as though our particle has a velocity greater than 0. And keep in mind, velocity could be negative. It just means that we're going in the reverse direction relative to whatever our forward direction is. And so, for example, if we took this particular point over here, we can approximate the tangent line to look something like this. And over here, it seems as though the slope of our tangent line is negative, right? Our function looks to be decreasing. And so over here, we would say that the velocity is going to be less than 0 in this particular instant because it looks as though the slope of our tangent line is negative. And if we were to take this point over here, it seems as though the slope of our tangent line is very positive. So here we could say, v is much greater than 0. And so that's kind of how we could analyze the velocity of a particle using a position time graph. And over here, I drew another kind of arbitrary graph. This one represents the velocity of a particle as a function of time, and we can use this to actually analyze the acceleration of the particle. So let's go ahead and do that. Okay, what's happening? Okay, let's go ahead and take this particular point over here. So over here, it looks like we have another local maximum. And so the tangent line may be a horizontal flat line, or it looks to be a horizontal sort of flat line. And with that in mind, we can say that at this particular point, the slope of this line is obviously 0, right? So the acceleration, or the instantaneous acceleration, is going to be 0. That doesn't necessarily mean that the velocity is 0. It means that at this point, we're moving at a constant velocity. So here we could say that we're moving at a constant velocity. And then that kind of logic could be applied to this particular point over here, where again the tangent looks to be horizontal. That's not very properly drawn. So it may look something like this. Again, over here we would have the acceleration being equal to 0, and we would have a constant velocity. What about at this point right over here? So at this point, it looks like our tangent line kind of has a negative slope because our function seems to be decreasing. And so at this point, we can say that the acceleration is less than 0. So what that means is that we are kind of accelerating, but in the opposite direction relative to our positive direction or relative to our forward direction. So it doesn't necessarily mean that we're decreasing in speed, but it just means that relative to our forward direction, we are essentially slowing down, right? We're slowing down relative to the forward direction, or we're speeding up relative to the backward direction. And at this particular point over here, it seems as though the tangent line is positive. That's okay, yeah, good enough. The tangent line looks to be positive at this point, or the slope of the tangent line looks to be positive, rather. And so over here, we could say that the acceleration is greater than 0, so we could say that we are speeding up in the positive direction, right, or slowing down in the negative direction, just depending on the context. And so that's kind of how you would analyze these different motion graphs using the derivatives. And if you're taking a physics course that isn't necessarily calculus-based, it's very nice to have a bit of calculus knowledge in order to understand how to interpret these graphs using kind of the basic principles of calculus.